Alright, so before we reach this part of the discussion, I assume that we have already, or you have already read through the reactions and properties of alkanes, alkynes, and aromatic compounds, which are all basically hydrocarbons because all they have are simply hydrogens and carbons. But at this point, we will be discussing classes of organic compounds that contain more than just carbon and hydrogen. And so, for the first families of that, I will put them in the name RX compounds, and this is actually a set of 3 families, and I just give this name RX compounds by myself, so you wouldn't really see this in books or references, but I prefer to use this. And the major disclaimer here is that the X here, unlike unlike the way we use it in general chemistry, is not really just halogen. Like X can be chlorine, fluorine, bromine. No, I'm going to use X here in the context that X can be any of the following. First, it could be OH. Second, it could be an amino group. Third, it could be a real halogen, or what it's usually known to be. Right? So, if we have ROH, right? If X here is OH, then we have ROH. So, ROH would be the family of alcohols. Now, what if X is NH2? We get RNH2, which would give us the amines. And of course, R attached to a halogen is an alkyl halide. So, now, before we go further, let me try to draw several examples of this, because we could actually classify them based on how many carbons are attached to the alpha carbon. Alright, just to recall, for example, this is the carbon, and this is the functional group. For example, we have alcohols, we have the hydroxyl functional group. So this is known as the alpha carbon. So there are several types of, for example, alcohols based on how many carbons are there around the alpha carbon. So if we have none, then we call this, of course, a methyl alcohol, or a methylamine, or a methyl halide. In this case, this is methanol, right? Now, if one of those hydrogens turn into carbon, for example, this one turns into CH3, then we say that it is primary, because that stands for how many carbons. This one stands for how many carbons are there attached to the alpha. Then I think we know where this is going. So if another hydrogen turns into a carbon, we get a secondary. Then finally, if the 3 attachments of carbon other than OH are all carbons, then we get tertiary. Now, why do I have to group them together? Because these ones have, of course, they have a common structure. They are attached to a certain functional group by a single bond, right? By a single bond. Then, of course, they have other than the common anatomy they also have a common reactivity. So in order to justify that, let's magnify the structure, or the generalities of what they look like. For example, I have here R, and of course we have a single bond to the X. So R single bond X. Now, if you would look at these functional groups, whether the functional group would be OH, NH2, or X, all of these atoms, oxygen, nitrogen, or any of the halogens, they are all electronegative. Oxygen is electronegative, nitrogen is fairly electronegative, and halogens are also electronegative. So what happens? They like electrons, they pull electrons towards this way. So then this functional group would have a partial negative charge, and of course the R here would result to have a partial positive charge. then if we take this R as the point of interest, then if we have a reacting group or an attacking group, of course, between a nucleophile and an electrophile, the one that would like this positive is a negative one, and of course, that would be the nucleophile. So, in case that the nucleophile attacks R, what happens is that the R must let go of X, and it should be easier for X to do that, because X would be like, hey, you know, we have 2 electrons, we are sharing 2 electrons. If the nucleophile here is offering you electrons, then I would gladly go away and take both of these with me. So it's as if the nucleophile goes in and the X goes out, or we say that it leaves. So from here we could derive certain terms for this. This R here, wherein the nucleophile attacks and X is previously attached before it goes to leave, we call this the substrate. Alright? Then, of course, obviously, this is simply what we call the nucleophile. And this one, this X here, which leaves once the nucleophile goes in, or which can actually leave before the nucleophile goes in, we will discuss about the difference of what I said. This X here is what we call the leaving group, simply because it leaves at the end of the reaction. Alright? You won't see it attached to R after the reaction is done. So, if we try to see the reaction mechanism here, it's as if, for example, we have here, this is the R is A, X is B, and this is C. So it's as if at the start we have A, B, right, bonded together. C comes in at the end, B goes out, and A bonds to C. So obviously this is substitution, not addition or elimination. So here we can see that we have already supplied the attacking group, what kind and what scheme. So we can say that Rx compounds in general can react by nucleophilic substitution. Nucleophilic substitution. Alright, so I hope that's clear. Now, there's something more than just nucleophilic substitution when it comes to alcohols, amines, and alkyl halides. For example, let's go back. But this time, let's be more specific. For example, I have here an R, then we have a C, then we have X here. We know that this is the alpha carbon. Well, if there is anything else attached to the alpha carbon, I mean a carbon attached to the alpha, we call that the beta. And let's say that this one has a hydrogen. Of course, this one also has a hydrogen. Now, there are certain reagents, for example, in a base, and actually we have to realize that bases are the primary reagents in this introduction or in this type of reaction. The base, you know, if we take a review, we could define a base as either hydroxyl donor, proton acceptor, or lone pair donor. And in this case, we will use its aspect as a proton acceptor. So for example, I have a base here. We know that once hydrogen loses an electron, it is generally a proton, right? Because, you know, only one proton would be left once one electron has been made. One electron has been taken away. So if the base attacks this one, what would happen? The base would take away the hydrogen, and between the battle of carbon and hydrogen, the one which is more electronegative gets the electrons, right? And of course, the winner here would be carbon. So once the base wipes away the hydrogen, what would happen? Since carbon wins in electronegativity, it will have a negative charge. Then let us not forget the partial charges here again. So what do we see here? We have a partially positive carbon, we have a negative carbon here, and we have here an X that is willing to leave. So what if X leaves? We are left with not just a partially positive one, remember, when X takes away the bond, when X leaves, it will take away both bonds. So as a result, when X leaves, so this is step 1. We can say that this is step 1, or the first thing we talked about. Then this is step 2. So what would result is X would be really completely negative, and as a result, the carbon loses its electron. It will be completely positive. So we have here carbon in the beta, which is negative, and carbon in the alpha, which is positive. Since we could interpret this negative charge, remember, one whole negative charge is 2 electrons. Well, carbon in the beta would be like, hey, I have 2 electrons, and you're positive, right, alpha? So what would it would do is it would just use these 2 electrons to form another bond, and that would be the pi bond between the alpha and the beta. Alright, so in short, base attacks the beta hydrogen, then after that X leaves, and after that a double bond is formed. So look at that. It's as if, for example, we have here X, which is B, then all of this, which is A. What happens? At the start we have AB, and at the end, what happened? B separated from A plus B. So this scheme here, alright, I'll repeat just to clarify. We have AB here at the start. RCC is A, then X is B. A and B are bonded, right? But then X leaves. So what happens to AB? It will be cut into A plus B. So this scheme here is elimination. And since the first target here is the beta hydrogen, people would actually refer to this mechanism as, with a complete name, as beta elimination. So in short, RX compounds can react either by nucleophilic substitution or by beta elimination. Alright, again, RX compounds can react either by nucleophilic substitution or beta elimination. Now that we have discussed about the general mechanism of RX compounds, or mechanisms that is, let's go now to certain aspects of RX compounds. Since I said that RX compounds have R single bonded to X, there are possibilities, for example, that the R would be bonded to X, would be bonded to Y, Z, and let's say another substituent A. And they might not all be the same. Alright? So if we draw them in, if we try to draw this in 3D, let's say X would be wedged, or wedge is facing out, then Z is broken lines, or it would be facing the back. It could actually have an isomer, a review on stereochemistry, wherein it would look like, it's as if this compound, let's say this compound A is facing itself in a mirror. We have the exact same compound, but there is a difference in the placement, because no matter how we rotate this compound B, it will never look like A, and it would be very complex to explain this on video. But maybe if we have review classes on this, I could use a figure or explain or draw this further. But the point is, this compound A is not exactly equal to B, but they are what you call mirror images of each other, because it's as if they are facing each other in a mirror. But then again, if I have this hand and I have this hand, even if they look alike, so it's as if this is A, this is B, they look similar, right? They look similar. They're symmetrical in a way, but they are not the same. They cannot be placed over each other. They are not, okay, the proper term for that is not superimposable. You cannot superimpose, or you cannot place one exactly over the other then expect that they would look exactly alike. And so this property of a certain compound to have 4 different substituents and have a mirror image of itself, that property This is an adjective. This is called, I know, this is a noun, chirality. And the adjective of any compound which has chirality is chiral. A compound with chirality is said to be chiral. And in the other way around, if it's not chiral, you call it a chiral. So here we have two chiral molecules which are mirror images of each other. Alright. So if they are real mirror images of each other, we call them Enantiomers. But if they are, if they are identical, but they are not mirror images, again, this would be clearer if we had more avenue to explain this. But generally, if I say that they are not mirror images, they look exactly the same, but they're not, but they are furthermore not mirror images, we call them diastereomers. But then again, there's an addition to that. But before that, I think it would be nice to go to the nomenclature, or not really nomenclature, but a system of naming. We call this the Cahn Ingold Prelog, but the name of the sequencing is not really known much. Just for Cahn Prelog, Cahn Ingold. I forgot the Ingold in middle. So it's actually Cahn Ingold Prelog rules on sequencing. So what do we sequence here? We actually sequence the substituents of a certain carbon X. For example, I draw here X. Then I have here, let's say, I have a hydrogen here, and I have fluorine, and then a chlorine, then a, bromine. Here we have optical isomers. So for example, we have A and B. So how do we know which of this can be designated as S, or which rotates a plane of light in a clockwise manner, alright, and which is R, which rotates S is counterclockwise and R is clockwise, because we know that if we have enantiomers, we have diastereomers, we have here chiral compounds which we reviewed in stereochemistry, or we talk in stereochemistry as optical isomers. They have the ability to rotate a plane of polarized light. So if they are able to rotate a plane of polarized light, they can either rotate it counterclockwise or clockwise. So if counterclockwise, again, we designate the descriptor S, and if clockwise, descriptor R. Now back to the Cahn Ingold Prelog. So how do we know if this, for example, we know that this is chiral. It has 4 substituents here. But the question is it S or is it R? So this is how we're going to determine whether it is S or R. So first rule, you must know which of this is the heaviest, which is heavier, even heavier, and which is the heaviest, and which is the lightest, whatever. So we assign numbers, alright, and we assign number 1 to the lightest atom. So the lightest of these is obviously hydrogen, and followed by chlorine. Then this is fluorine, then by chlorine, then by bromine. So meaning that from 1 to 4 we go from light to heavier and to heaviest. Then the next step is we must put number 1 at the back. I think it would be nice if we have a kind of imagination here. But let's take for example, we know that H is facing us because it's wedged, and F is facing the back. So it's as if for example, this is the front, alright. I'm pointing to the front, so this is the front here. So meaning, if I have here 3 substituents, Cl, F, and H, the one pointing at the front is H. So let's say this is H, right? This finger here is H. Then the one facing the back is F. This is facing the back because this is front, this is back. Alright, then this is chlorine. So how do we rotate it? We put this hydrogen at the back. So what happens? The chlorine, which used to be here, it goes at front, and the fluorine, which used to be at the back, it goes to the side. So how do we draw that now? So I hope you get the imagination. So hydrogen goes here at the back, chlorine goes at the front, then fluorine from the back goes to the side. Alright. Then bromine, since it's at the top, nothing changes. So what happens now? Hydrogen is the back, then we have fluorine, chlorine, and bromine. Next step, you make a direction from the smallest to the largest. So for example, we have 2, we start from 2, then we go to 4. Then we will see if it's rotated counterclockwise or clockwise. In this case, it rotated in what manner? Counterclockwise. And so in that case, we assign this as S. Alright, so we assign this as S. So we're going to use this stereochemistry later on.